Right, hello everyone, welcome to another stream. How are we doing? So, last stream we was refactoring the shader to support clusters that are 4 cubes instead of 2 cubed. So now each thread group is a single cluster, but there's 2 waves, right, of wave 32 that process 64 elements. So we're simply just finishing this graph today and hopefully moving on to the next shader that needs refactor because of this change. So yeah, let me just continue down here then. So it's at the end of the shader. I realized as well that we have to create the child nodes as well. So we got to this point here. So let's take a gander. And what's going on? So at this point of the shader, Yep. So I guess let's just have a quick recap of what this shader does. So it builds the initial shape of the cluster tree. So the cluster tree is this, basically, right? It's a 4x4x4 of spheres, and each cluster has a 2x2x2 of children, and those point to more clusters, basically more of these guys. Each sphere in here is represented by a 2x2x2 of spheres in the higher resolution cluster. Because you see it's 2x2 here, and it's half of 4x4, right? So this shader is essentially taking a list of like operations like placing down ellipsoids and cubes and filling them in with spheres, basically. So at the end of this iteration here, where we've gone over all the sort of edit operations that apply these spheres into that cluster, we've got all the information. We just now need to store it inside the cluster here. Allocate children if needed. We need a barrier, right? So yeah, this allocates the children, and then we'll need to create their nodes as well, something like that. So we've got this children bit set. So we'll probably need to put like at this point this thing won't be created, right? So you need to say we need to communicate across the waves to know. So we need the complete bit set. Oh, but we've already ordered it in here. So I guess this could be the communication across the waves, although it would be quicker if it was in LDS memory. Probably. Maybe. It might just be okay just to read it back, but I've got my LDS here. So we'll just put the children bit set. So where's the initialization? Here's the initialization, obviously. Children bit set. So we'll clear that out. What the crap happened with all this syntax highlighting? Well, I guess we're going back to... okay. Let me close my... Let's close that file, maybe? Damn, that broke. Hey there, that guy, Duru. Yeah. It's coming along, man. Just, we've kind of made this new plan, and initially it was quite different, but it's ended up being like closer to what our initial implementation was. So we've just been able to refactor our current implementation over to this new one. And what's great is I've gone into even more detail for the stuff that comes after this. So it's sort of all the features that we want to add, like skinning and painting these volumes, has been sort of planned out now, basically. So it's cool. So I know that this implementation is going to be a lot more solid. But yeah, going well, man. How's your stuff going? Are you working on anything? So I've probably got a... I guess I'll close the editor down. Maybe I'll quit the document. Ah, that was good. Right, syntax highlight is back. So we want to store... Oh, here it is. Yeah, store an LDS memory. And because it's an LDS, it might be better to atomic store it. That's a good point. Where's my LDSs? Yeah. Right. So at the end of the shader, we've got to share this bit set thing. So we'll do another OR. Right. Then we need a barrier because you've got two wave 32s running at the same time, and they're not running in lockstep. Right. Usually in a shader, you've got like 32 threads running in lockstep, processing the same instruction at each time. But because we've got our local group is 4x4x4, which is 64, and we're running in wave 32, they're not in lockstep. So we have to put a little barrier up to say, hey, wait here. Wait here if the other wave, wait here until all of the waves reach this point in your thread group or dispatch group, and make sure the memory is synchronized as well. So we synchronize the ODS, and right. So now, what this means we can do is we can atomic load the this, and really what we should say is that, hey, if you're the first thread, like we do up here, if you're the first thread in the group, right, load the child bit set, and then we want to be able to do we want to allocate the child nodes, and then we probably want to put another barrier here, and then if we have children, if we have any children, then probably set them all up in a multi-threaded way, right? So you take advantage of all the threads. Oh, what did the previous lack? It was mainly the fact that our cluster size was 2x2x2. So mainly it was 2x2x2, and that was causing it so there was in a 256 cube volume. Wait, where is it? 256 divided by 2, that one. Yeah, there could have been like 2 million clusters to process, just for a single volume. So, or they could be up to this many. What's the way of saying it? Yeah, but probably in reality there's far less. So they ended up being like 500,000 in the test that was running for the 2x2x2 clusters. But because we're doing 4x4x4 clusters now, and a 256 volume is 64 cubes, so there's only there's 8 times less. Wait, it's not okay. I'm saying it. Yeah, so in 2x2x2 there's 8 times more nodes than there is in a 4x4x4 cubes of spheres. So this means when we're doing occlusion culling, we'll be culling fill-on instances, right? So we cull the arms if they're occluded, then we don't draw them. If they're not occluded, we'll try and render them. And then, so there's the instance level. Then inside the instances, there's a bunch of clusters, and then we'll occlusion cull each of the clusters. If they're visible, we'll render them, and if they're not visible, then we'll then we'll obviously not render them, right? So basically, there's like probably 8 times less clusters to process. So it was like 500,000 after simplification for the old stuff, and maybe, let's divide by 6 to be generous. So maybe there's 83,000 to process per volume instead. Yeah, maybe there's probably less than that. But yeah, maybe we can. But yeah, so it should be a lot quicker to process, basically. Oh, and that's the other thing as well. The way my previous design worked was that we were going to like launch from the leaf nodes at the bottom of the tree, and we was going to check, hey, is this leaf node? Yeah, because the thought was we have more threads, right? Or you get better thread occupancy if you can launch across all the leaf nodes, right? All your threads could be, well, not occupancy, that's not what I'm saying it. If you launch across all your leaf nodes, you'll be using all of your compute units basically right away. And you'll be able to process these guys, check if they could be rendered. If they can be rendered, then we'll just go and render it. Or we'll put it into a queue and we'll go to render it later. But the problem with this approach is that if you had 500,000 nodes in a volume to process, or in our new case 83,000, right? You'll have to go over all 83,000. Whereas there's a different approach, which I learned through watching a video on YouTube, which means you start from the root node and you check if the root cluster, which is like, this is L0, right? Just the lowest level of detail. And this is L1, right? These are L1. So every single time so these are the supermassive spheres, which represent the whole volume. But if this cluster is occluded, right, fully occluded by some other object in the game, you don't need to dispatch any more threads to process these ones and beyond, right? So you literally say you only processed, in this case, one node. But obviously in the real world, you'll probably have to go down a few layers before you have to go down maybe a couple of layers before you start occluding stuff. Or maybe just one. But yeah. So it should mean that we should process far less data. And this should actually be possible to pull off, basically. Is 4x4 optimal for this? So possibly we might have to go up to 8x8 at some point. But I think 4x4 is but we could be wrong. 4x4 could be fine. Because that gives you 64 spheres. The old one was giving us 8 spheres. Right, you was culling 8 spheres at a time, and if you didn't cull, you was rendering 8 spheres. This one gives you 64 spheres with 4 cubed, right? But 8 cubes gives you 512. So that just feels like such a big number to sort of chuck into the renderer if we miscalculate something. So maybe 4x4 is the sweet spot. Is this Little Planet 3? No. Not at all. Have you seen that game already came out on like PS3? Or was it PS4? I think it was PS4. Okay, so here we need to actually allocate. So where's that allocate that I did for the spheres? That bump allocate thing. This is the old code. Here it is. The free indices. This is it. Beautiful. So this one was the old code for the free spheres indices, like allocator. So this is just a cluster nodes, I think I called it. Yeah. Cluster node free indices stack count. So basically we have an array that's pre-allocated with all the free indices, and when you get back a free index, it actually has like 8 slots. That is a contiguous array of 8 elements, and that's where so there's an index into the. Sorry, this gives you a slot index back into the free indices array. So let's just get into there. And this gives you back the child nodes, the children. Cluster node start index. So we have 8 child cluster nodes that get allocated all together. So it's nice and easy to write a custom allocator for. It's literally just divide an array into 8. Just divide it by 8 into 8s, right? So we're just going to store that index into the cluster, and then we do a wait here for both ways in the thread group to get to here, and now we get the bit set. So you kind of want to just say if. So you need to get your sphere index, maybe 0 to 63 inclusive. Right, so if the children bit set, so if you have any, okay, if children bit set and so you kind of want to say if this is less than 8 and something like that, then this means we can set up the child nodes like 8 threads at a time, basically. Still not getting like full utilization in anyway, but it's better than doing one thread, doing it all. So we need to set up the 8 nodes, 8 child nodes. So this is where the root node got set up. So we need to do this. So there's a start index. So we can pull that start index in. So atomic load, the start index, and we work out the actual like child cluster index. So it's that plus cluster sphere index, and then we can just simply throw that all in there. So the location, so this is LOD, so whatever the current LOD is. Here it is, cluster LOD. So the current cluster is LOD plus 1. And then this is a 3D XYZ coordinate. So we've already done that here. Oh. Past me did it way better. Is that right though? It might be times 4 because we're doing 4x4s now. Just have a think about it. So if you're on left, yeah, it's 4 more plus the, yeah, that's right. Yeah, I think that's right. Because so if you're at level 1, so it's not level 0, right? You're at so second level, level 1, you've got, at that point, you've got 2 clusters and you're reaching 8 by 8 by 8 spheres, right? If you're in index 1, wait, you split them into 2 by 2 by 2s, isn't it? It is just... No, this isn't right. Is that child index thing? Yeah, we should probably take this. We should call it, probably just write child index. Make it a little bit clearer what this code means. But I'm thinking with, when you take the child index and like flatten it back out, I've done that. Sorry, there's some other code. I've done that in the past, where we take a flat index from 0 to 7 and map it into 3D. Here it is. But which way do we need to do it? So if you're on level 2, let's draw this out. So I've already got drawing over here. So this cluster, yeah, so this cluster here, it's going to have a 2 by 2 by 2 of children. Which means when you mod 2, wait, what are we doing? So you're left, yes, the node, if you got this node here, which should already have maybe so it's got a 1, it'll be a 4. Yeah, that makes sense, but it's like the remainder part. Oh, it's the parent one. Okay, yes, it's a remainder part, isn't it? So it'll be that then times by 2. So what's times by 4? Because that'll give you, because there'll be 4 in this child one. So maybe this one points over to here or something. You're given the location for this child node here, for instance, in a 3D grid. This one has 4 spheres going across. So you would instantly do so you'll be 1 here. So it'll be 0, 1. Then I guess just times by 4 in it. But then I'm not sure if this part is correct. So this is fine, right? Copy this over and just these over to here at the end and do times by 4. That's fine. But is this times by 4? So this case is when you've got a node location where a node location on the, say if it's better if we're doing this guy over here, right? And so you would have had, this would have been given a 4 on the X because of this part here, right? That goes there technically. So you'll need to take this and then times it by 4 for a child. So let's say you do this one, which has got nothing on the these you'll have 4, then another 4, 4, then another 4, right? But down in the higher level, right? In the higher resolution. Yeah, 4, then another 4. So if this was just 4, you need to multiply it by 2. All right, because it's an octree. Okay, so I'm glad we got that right. Just takes a little bit of thinking. That's what it takes. So that's the correct coordinates when we go into the higher resolution. Just got to get the precedence thing. Watch out for that. Cool. Right, so there's the coordinates all set up now inside that cluster. I'm thinking about other threads accessing this, so it's going to have to be a store. Unfortunately, atomic stores. because different compute units can be accessing the same memory as soon as we poke them onto the we have to poke them onto the ring, but the queue. Do you need parent between the parentheses? Right. Between the division. And the division. Because I only see the division, like they're comma separated, right? They're a separate argument entirely. I don't see the problem. There's only one of those I can see on screen. Oh, I see. Right, fair play. No worries. So these new child have no children. They have no spheres yet because they're yet to be processed. They have no exclusive LOD spheres. They have no children of their own, right? Excellent. Right. So now we've nearly done this. We just got to push it on the queue. So what's really cool about this solution is we've got this sort of like process queue at the top of the shader, and we've just dispatched a bunch of these, and they just keep running until they're finished, until the queue's been completely exhausted. So we have to push on this queue. So we've got to do something with this tail, and we've got to like do a bit of poke in the buffer as well. So I think there might need to be two. This is where I've got to figure out how we're going to do this, because if you atomic add onto this queue, you must put an invalid value in the queue. So if we do an atomic add on the tail index, we'll get back the insert index. And then we'll, we atomic store in the process queue at insert index, right? And you store in there the child index, child cluster node index, right? So it's awesome. So this is other threads. You can just come and pick it up and start going, working on it, right? New haircut, yeah, man. Yeah, going on holiday, so need a nice new haircut because it's going to be baking where I'm going. And plus, it's getting a bit long as well. Everything was getting long. My beard, my hair, so all had to go. So it could be the thread to atomically thank you, sir. Appreciate it. So maybe we fill the buffer with -1s. Right. So I've got a shader or a backend function to do that already. So when we do this sort of construct leaf spheres, I think it's called, Just got to find it. Right. Well, you want to... I kind of deleted a line here that kind of did something like that, but on a different buffer. But I think it's called like memset U32. Excellent. So just put the resource ID in there. That will be the process queue. And we're going to then... the word we're going to use is U32. So this will mean then, obviously have to zero a whole buffer or something, but or sorry, one a whole buffer. But then it means we don't so we just then it means we don't have to fiddle with something here, because at this point when you've added and not stored the value, another thread could have taken it potentially. So when it reads from the process queue, wait, why is there a store there? Oh, it's storing that in the LDS, right. So we actually missed an atomic load here. So what you want to do is say U32 cluster index is one we're going to process. But we'll do the lovely C thing, right? Cluster index, oh wait, I need to do the atomic load. I can't believe I'm doing these spin locks on GPU. It's gonna be lovely. But yeah, so we'll just simply say like, spin. Wait, we're gonna wait until it's not equal to while it's equal to U32 max. Yeah. Then it's safe. And the value root is safe. So now that solved that problem, which is really great. So I think we've gone and done this shader now. What I want to do is probably take another sort of look over this shader, just double check we've done everything we wanted to. But the job of this shader, so we got to the top, we'll read the thing here. So shader builds the initial shape of the cluster tree with all of the leaf nodes and leaf spheres placed down. English. Each thread group processes a 4x4x4 cluster at a time, takes a cluster from the process queue and runs the and evaluates the list of edits over the cluster. Then we push its children onto the process queue if it has any. However, the shader is not finished the following aspects parts of the tree. Low LODs of the tree are not generated, no simplification, and there might be some dangling child nodes dotted about. Cool. Okay. So basically the way we launch this shader is a bit weird, but it's pretty cool at the same time. So a GPU, right, has these things called compute units. And it doesn't just have one of these, it has multiple of these, and these things they're basically like they have a bunch of they have space for like VGPRs and SGPRs, right? Vector general purpose register, scalar general purpose register that can store integers and floats of 32 or 64-bit in size sometimes, maybe 16 bits as well. It depends on the hardware. But these compute units can execute a single shader. with 32 threads. But when I say threads, is because it's basically doing. It's got a it's got like an ALU, like an arithmetic unit, which can operate on 32 wide, 32 wide SIMD, right? So that's why things run in lockstep, right? So, and to like hide latency, another key factor with compute units is when they need to do some sort of thing with memory, what they do, if they need to load from memory and it's not in cache, what they'll do is they'll like basically switch out to another another shader and continue running that one, right? Until it hits another place where it has to read from memory, and then it will go and run another one. So it does a good way of hiding latency. And I think that's somewhere about 10 on RDNA GPUs. So what's really great is you have like, on my GPU at least, you have 28 of these compute units, which means you can run, you can run quite a lot of shaders kind of at the same time, right? Considering they switch out and all of that. SIMD. Yeah, SIMD, that's it. Yeah, single instruction multi-data, that's right. So what we do is quite different. Like the way they want you to do stuff is they want you to basically say, hey, you can imagine like a 2D texture or a 2D grid of what they want you to do is just say, I've got like they want you to launch over every one of the pixels, basically, and just say up front, hey, I'm launching over all these pixels. So you go, I've got like, I've got 1920 by 1080 divided by 8 because that's your local group size or something like that. And you dispatch threads, like enough threads to cover that whole space, right? But the problem with that design is when we're trying to process a 3D volume of 256 cubed, right? That's 16 million threads that are needed, right? Threads. We've divided by 32. That's 500,000 compute units that need to load in the shade. Well, I guess start the shader, shall we say, right? Just to find out that it doesn't, process a few instructions, or maybe, I don't know, 12 instructions or whatever it is. Find out there's nothing there, and then it kills the thread, right? And it has to, so if you have a small volume that doesn't like really need all of those threads to be launched, then it's a big waste. And actually, furthermore, it's more threads than that, because it's 256 cubed is the highest LOD, and we actually have like a kind of like a MIP chain going up to the lowest level of detail. So there's actually even more threads than this, somewhere about 50% more. So to solve this problem, we're just thinking at it from like a hardware point of view, and we just say, now this is where Vulkan doesn't help us in any way whatsoever, and we're kind of on our own, and that's okay. So we've got to figure out how many compute units are in a thing, but we basically just launch. We just launch the groups. Like we just launch. We try to launch as many groups as there are compute units, plus the amount that it can switch between, right? And then we simply just have a ring buffer that we pull the data off. So that means our waves are going to run for a long time. I'm not sure how that's like on the hardware, right? But it means we shouldn't be scheduling waves to happen, and then they basically end up yeah. So maybe it's good, maybe it's not. But this is what we're trying out. So we're just processing from like a queue that we just pop on and push off basically. We'll see how good it is. We've got numbers, right? So it's not like I'm shooting in the dark here. I took a screenshot of the previous implementation. So we're going to compare. So yeah, we just pop off the ring buffer, the next cluster to process, and we go full ham. There are more optimizations I can make them but I want to test out this new approach. So yeah, basically we're just popping off that ring buffer. That's what the code looks like. Joyful. You need to wait here because there's two compute units running at the same time here. Well, not at the same time. There's two instances of the shader. They'll be running in the same compute unit. But they don't run in lockstep. Because there's two wave 32s that are needed. So we need this dispatch group wait here, and we wait here for the we wait here for the first thread of the first wave to load the job. So it's going to add the fact that it's waiting. Going to get the head index. Going to get if it's equal to the tail index. And we've finished. And all threads are waiting, we return. If not, we just go back up and continue and keep going until there's one available. This one is going to then do a compare and exchange. We're basically saying we're the guy who's added 1 to this number. And if we're the guy who added 1 to this number, then we take it and we wait for the value to be available for us. And then we store that in LDS so that the two waves can have access to it. LDS is local local data storage. So we've got the cluster index in there, and we drop the count that we're waiting for. Could this be a bug? Yeah, it could be a bug. Because you want all of them waiting. Yeah. You want them all waiting. Oh, you bugger. Yeah, what you want to do, I think, is this. Because, yes, you want to say, hey, I'm not waiting anymore. And then go, oh, yeah, I'm waiting. Maybe what's best is so we do something like this. So we load, if we're all waiting in here, then return, but could you end up... So when you do a break here, I just think there's a time where I still think there's a atomic bug here. Do you need like a second variable to count up to save you're all sort of like, because one could come... Oh wait, no. I already verified this. It's simple. Very simple. It's very simple. If the last thread came here and incremented this number, I think this is right. Yeah, so the last thread came here and incremented this number. And then you've done a load. Actually, it might not be that simple. So the last thread came and incremented that number. Yeah. This needs to go here. Then we do another add again. All right, that'll work. Yeah, so what we can guarantee is when the threads came here and added it, the last threads came here, like, no other thread is going to be able to put more work on the queue, right? So by the time you get to, when you get to here and this ends up being true, and this ends up being true, no more work could be added, right? But what could happen is, so your last thread hasn't reached here yet. Okay. You find out that this is not true, right? So one of your threads gets to here, right? But then you find, but let's just say then your last thread, but let's say the last thread like stops here for some reason. Because it gets switched out or something, right? To another instance of the shader and gets run on the compute units. Then the last thread gets here and ups this number, right? The other guys still would have loaded. This would still, this condition here would still not be true, and the other threads will come past here as well and subtract from the waiting count. So they wouldn't actually be, so it's completely safe, right? You'd only get into here so long as all of your guys are spinning around this area here. So it's completely safe. Which is good to know. Hey there, Harry Dree, how's it going? Doing good, man, doing good. Just doing some crazy atomic stuff on GPUs, which is probably a bad idea, but we're giving it a go. So we're just doing a lock-free queue system in a shader. But yeah, so that's completely safe. So where did we get up to again in this? So we did that, compare and exchange, did the spin. Yes, usually this stuff is like probably not a good idea, but atomic's all you have. But there we go. I haven't needed a video editor. Not really. I haven't really got any cool stuff to show off yet. But yeah. I appreciate the ask though. So reset break. Yep. Okay, so that's all good. Now get to the cluster processing. So we get the cluster index from the LDS, right, because it has to be stored in there because there's two threads running on the same data. Yeah, two separate compute units of wave32 are processed in the same cluster. So you pull out the cluster node that you're processing, right, you get the LOD. This stuff is all correct. I remember double checking it and it was fine. Yeah. So the whole task of this for loop here is to go over all the edits, which basically paint inside the 256Q volume. You got a has sphere bit, and you've got a has exclusive LOD sphere bit. Because this cluster is at a specific level of detail, and it either has a sphere that's been painted down in it or exclusively painted for this LOD, meaning that if only when we render this LOD will this sphere show. That's what that one means. And do we have a child node that we need to allocate? Right, did we end up using that? Yes, each thread gets a sphere basically. Right. Awesome. So that's some debug code, go over all the edits. This stuff is all fine. I think the so all this is doing is just checking to see if the sphere the sphere within inside the cluster, right? Where's the cluster? Here it is. So if the sphere that we're checking, right, doing 32 in lockstep together, if the sphere, if the sort of ellipsoid edit or the cuboid edit covers the sphere that we're processing, right? That's all we're checking here. I think the ellipsoid one is a little bit off. Need to check that at some point in the future, but it doesn't really matter so much now. Then we're saying if the target LOD that we're painting down is greater than the cluster, we're going to need a child node at this point, because we need high level of detail. If the target LOD is at this cluster, we check if it's an add or remove. We only really want to do that if it's an add, right? Yeah, let me double check that. Yeah, so it is, right, so it's higher. You've set it as if it's an add, you want it to be true. If it's a remove, you want it to be false. That is true, so that will just be fine. That's what that will be. So if the target LOD is equal to the cluster LOD, so we're painting at this LOD. If it's an add and it's an exclusive LOD paint, we set this boolean. If not, we set this one, right? And if it's a remove, we just do the other way around. So we could actually just simplify this, right? We can remove the branching, right? And simply just, you just have a boolean where you just say is add, right? So you just remove all the branching. So that's what we're going to have is add and remove operations for this thing, which would be cool. So that's greatly simplified now, which is great. Right, where did the music go? No music. So now this is at the point where we're going to turn these bits into bit sets and then pack them into the cluster. So we, shift them up. We do them. We mod it with 32 because there's two wave 32s, right? and the cluster is a 4x4x4, which means there's okay. So there's another problem as well where you only have 32-bit integers on GPUs. Really, you can probably use 64 nowadays. We're just going to keep using 32s. So you have two of those guys, right? One wave 32 does the low, does index 0. The other wave does index 1, right? So that's where we get the wave index like this. So that's why we mod it with 32. So we just, each wave packs it into a 32-bit integer. So we just orient it in there using the wave intrinsics, which is super nice. So then we do with the exclusive LOD sphere bits as well. Do with the child node, right? That's fine. Get the wave index. Use atomic store to pack it into the right place. Bear in mind, this should only happen on the first what's the way of saying it? On the first sphere of each, because otherwise you'll just be doing it 64 times when you. But maybe the. Yeah, I don't know. We'll see. Maybe the processor would deal with that, but I don't know. So we do the stores. There's only two happening then. On the two locations, and then we orient that into the same location. Because the children bits that would be spread across the two. Right, it's an octree of children. So it's a 2x2x2 of children. So the children bit set will kind of be half set on one wave and half set on the other wave. Right, kinda, I think. Yes, I think it does it like that. Yeah, so the first. Wait a minute. Yeah, the first two slices, right, of 16 are done in the first wave. So they only do the first half. So it all them into the same place. Good. Then we orient to LDS memory because I think it's quicker that way. Then we do a wait here because what we need to do is we need to do this. We need to make sure everything's written to this stuff here. Those two waves are written to that one there, right? If we're the first thread in the whole thread group, right? So to this point, like 63 threads will be inactive right now, and only one thread is going to do this. It's going to load from the child bit set. Wait, why does it need to load from the child bit set here? Wait, you only want to do this providing you have. Why wasn't this load done earlier? Right, providing. Because they could just all skip that literally, and I think we might have to put I might put a barrier down at the end. So something like that, right? So if maybe we put the barrier at the top because that'd be a bit. It might just be able to do a nice. Oh no, it won't because of the block end things in it potentially. Right, so if we have any children, then we'll wait here. The first thread of both of all of the waves goes through here, allocates a contiguous array of 8 child cluster nodes, and then it stores it. Do a wait again. The first 8 threads will possibly, if they're set, go through here. Yeah, we'll go through here, then do a load on that start index that we allocated. Set up the cluster. Right, we checked that, we know that's fine. Just set up the cluster. Yep. Then insert. Oh, we didn't do comma 1 there. Okay. Then insert in the child cluster into the process queue. Do a wait here for some reason. Well, maybe we don't need to do that. Now it might be okay to actually avoid that one. Yeah, so then we just go back around again, take off the queue, right, and begin processing the next cluster. So yeah, all the work is going to be done in this sort of for loop here where it goes over all the edits and stuff. Maybe in this allocation as well. Yeah, because you might have like thousands of these, maybe. Yeah, sometimes. We will simplify the list as we go down the tree, though, in future iterations. But yes, that's basically the shader. No manual ASM. You can't do manual assembly on GPUs. The closest you can get is manual SPIR-V. Let's delete all this code. This is the old version. Right. So after that is done, we build the occupation map. I don't think any of this changes in the shader code, but I may be wrong. So what the occupation map is just a bit set where each bit represents. It's a bit set where each bit represents a cluster that's completely filled with spheres. So we use this to simplify the tree. So it's really cool. There's some more intelligent things about it, but I can't be able to over-explain it. But yeah, it means we can basically do 2 samples and tell if a cluster is surrounded by other clusters. That's really great. I just got to be careful on the way we dispatch. So oh, we'll have to edit the code. So we go over all of the clusters, right? And we just want to write them in. But this only went over the leaf nodes. Maybe we can generate the occupation map in this shader too. Because all it wants to do is go over the... Yeah. So let's do that, because there's no point. Oh no, it's the leaf nodes. So a leaf node means that it's got no children at all. Leaf node means it's got no children at all. So I think we can just literally stick it here. So, and then that will kind of be great because that gets rid of another... Yes, only problem with the occupation map is you have to have a downsample pass. Alright, so we take that with us. Let's not delete it. Let's take it with us. Drop it in there. So cluster LOD to highest LOD. I think I've already done this. cluster LOD. What does this stuff mean? Okay. The same thing, isn't it? So that, first of all, that should be called construct. That's just not a good name. Right, sort that one out. So that doesn't have to be kept anymore. Highest LED clusters count. Don't think we did this one. Then cluster coordinate is the position of the node. Write some print code. Hey there, CatPaint, how's it going? OpenCL is a way to find the max compute units. It does. Yeah, we did search for that last stream, and someone did say about the OpenCL being able to do it, but then someone was arguing that wasn't a good idea that they expose it. For some reason. Max compute units. That's not the number, right? The maximum number of parallel compute units. Oh, wait, it might be. Workgroup executes on a single. Yeah, that is the number that you want. I want one of those CL units back with this number, you know. Yeah. How'd you get around it? You create a open CL instance, and you get the number. That's how you do it. Not a bad idea, right? Yeah, I don't think that is the number. Because if I do my Vulkan info grep stuff, right? I got 3. What does that mean? What does the documentation say that is again? Oh, there's 3 of them. Oh, there's 3 of them. Okay, got it. Maximum number of local workgroups that can be dispatched by a single dispatching command. See, it's a completely different thing. That's just the amount of X, Y, Z dispatch things you can do. It's completely different. It's all abstracted into these work groups in Vulkan. What I did to isolate was just include in a C file, then just declare a function in the header. There wasn't any conflicts. Relib and Windows conflicting, so I had to work around lol. Right. Not bad idea. Yeah, that works. Some other people do a different approach, right? Where they'll what they'll do is they'll just not include the headers, and they'll basically just forward declare everything they want and make their own header. Rightio, so this looks like it could work, right? Where we build the occupation map within the same shader. It makes it more complex, but away we go. We should tell the GPU, right? we totally need to make. We need to make, right, one of these, because this is just so dumb. Right, here it is. Define wait, I'll put in GPU shared. We want it forced to be in like when the compiler won't know like what it is. Or it might do. Will the compiler know? I didn't really fully double check that properly. Oh, let's get back to my shaders. What was I saying? Yeah, this bit set. It does an atomic load. Ah, yeah, no, it will know. It will know. Because it'll load the same thing, possibly. Yeah, it loads the same thing. Yeah, so it will be an SGPR. But still, I need that thing because it's just quite common, probably. Excellent. Define GPU force SGPR. Wave active min. Something like that. Just be more readable that way. So basically you're saying that you've got this value x and the compiler is going to see it as a VGPR, and you want it to be the same across all of those threads that are running in lockstep. So you basically just use this min operation across all the threads that run in lockstep, and it will put it into an SGPR. So when you do like an if statement on it, it knows the branch. It knows all threads either go down one branch or the other branch, so it can write compiler code. It can write proper assembly, which will basically branch instead of running both of them one after the other, like GPUs kind of do sometimes. So it speeds things up a lot, and it means it can allocate the registers differently as well. Like it can allocate the same registers that are used for this branch of code and this branch of code, which is really nice. But yeah, I don't think I need that here. But anyway, let's carry on with this thing here. So we go over all the clusters, blah 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 blah, cluster coordinate, fine. Yeah, I don't think there's anything that was different. What did we have that was defined? A thing called node. There's a midpoint cursor thing, but I think that's all right. We need the occupation map in the thing though. Yeah, we're right to the highest res one. That's fine. Right, so here's the occupation map. So we don't need this anymore, which is just amazing. This pass here. So let me just go ahead and move that over to the correct place. What else are we trying to do? Yeah, the sync code. Excellent. So we can delete this whole pass here. So now actually we can delete the other pass as well, the one that generates the indirect arguments. We'll look into that one in a minute. No, we might need to keep that one. Yeah, we'll see. Cool. So yeah, we basically just generate a bit set, right? The highest MIP. Sorry, the lowest MIP, right? The one with the most detail. Where each bit represents a cluster, And there's some repeated information in there so we can avoid. So we can do less samples later. So that's really cool, got that in there. This shader is to generate an occupation map in direct arguments for that shader that we just deleted. So I don't really need this anymore, but it also did more things. It did it for the refine step and the make persistent step as well. But those can just do a those can just yeah, those don't use indirect args anymore. So let's go to here and delete these indirect args. Now what we need to do is set up, we probably want to have another shader. So we've got this initialize shader, and this basically sets up the where's the midpoint cursor there? I guess I haven't tried compiling this yet. Right, but anyway. Okay. So we need to probably break this into two shaders and just launch them a couple of times. So you want to be able to say volume constructor traverse reset or something like that. Wait, so why? You need to traverse twice, right? Once in the simplification. I don't know actually, let me just double check. So let's just delete this shader, then we don't need it. That's what we came to. And we'll go to the next guys and figure it out. So we need to do the down sample. That is true. So this goes and does the down sample on that occupation map. Custom down sample because there's repeated data in it. I'm not going to go over this. We've done it in a past stream. Got a past streams many times. The code works. So it just does a custom down sample of the bit set, which represents, each bit represents a cluster that is completely full. Actually, this is slightly wrong. I just remembered. Where's the shader we deleted? Here it is. We've got this if statement here. This is an essential if statement. So we need to only do this providing that the cluster. So I was saying that if the cluster is full, but probably not a good idea. We probably should say, hey, if it's like 90% full. So you have the bit set. Here, this is the one that actually get down. Wait a minute. What about these exclusive LODs? Now here's what we need to do. So 0, 1. Then we get to use you want to count all the bits. I think it's like wait, let me find my guys. Do I have a way to count some bits? Crap. So I have to add this to the compiler. So this one gets you the least significant bit that's set. Use this one all the time. We want... Right, is that in the GLSL SPV GLSL 450 or whatever it's called. These ones. Right, it's like population count, bits. Oh, that's not it. Is it in these guys or is it in the standard SPIRI instructions? I'm not sure. Just gotta find it. Least. Just packing and unpacking. Find LSB. Find. They must have a quote unquote instruction for counting the bits. GSL count bits. Bit count. Alright, what does this compile out into? See, they've got find LSB and find most significant bit. In standard SPIRI. Man, they added the counter buffer nowadays. That's to support structure buffers. Nowadays. Crazy. Alright, so bit field insert and all that. Bit count. It is one. I haven't used this. Should drop this guy in. Just think about it, did I even update my... Must be a scalar or vector of integer type. Or vector, eh? Oh boy. Oh boy. But yeah, I think we can just do it for... I guess I'll put them all in though. Yeah. But yeah, this is something that we need. Because we need to be able to say bit count and then like get the number of bits. Anyway, I've lost my thing now. Right, let's hop over to the new terminal and add that into the compiler quick. Did I even push up my latest changes? I did. Right. So basically we've got libhmaths, which is the sort of library we've got, and it's got C implementation and a so for regular C compilers, but it also the compiler sort of can implement these functions as well internally. So let's put the bits and bobs we want in. The number of bits set to 1. Right. It returns a count of the number of bits set to 1. Right. So we're just going to hop over into the libhmaths vector. We're going to find those these ones Is this assembly? No. Just see. Um. I think his return types are a little bit off. I made them just return U32s regardless, wouldn't it? A little bit inconsistent. Effort. I won't bother changing it. You need to enable the data type anyway to use it. Right, so now we've got them in the header file, we'll just implement them now. Wait a minute, but we should have implemented this. We have to implement it on, right. We'll implement these in, on Windows and Linux as well, they're quite easy, bit count. It's just pop count, isn't it, basically? If you're familiar. So I think it's pop count on Linux. Right, where's the GNU pop count? Or bit count? Built-in pop count, it does exist. Why things like rocket science to find via Google these days? Complete bloody rocket science. Right. Windows pop count. I just need a U in there and be a tasty, tasty word. Right. I probably don't really care about the short version. When is that going to technically be better? So yeah, we just want to return. Right, there we go. Cool, so we just repeat that in all of those. Except the 64 one, it needs a bit of a different one. So we pop count 64. And for the Linux, oh man, I hate it when it can't. Right. This would be pop count 64, right? Oh, why is there so many underscores in my face? Pop count LL. Of course, they were longs, aren't they? Silly thing. Oh, pop count 8. Oh, CNT. No? Oh, it's not built in. What the crap is going on? It's an IBM thing. Fine. Crazy. Alright. so now we've got those in for the CPU side. We'll hop into the compiler and get those in. So based on my vague memory of this code base, I think it's in the internal code base. It's a thing called function many. No. This is in the public header. Cool. So we find bit LSB. Add a new one called bit count. Which means we have to find every implementation of this. Grep bit ms. So we need to edit. We need to add an abstract machine language thing as well. So that's a machine language and abstract machine language instruction. So that's our sort of high-level assembly that translates into SPIR-V later. So we need to create the abstract machine language instruction, and we do that in, well, there's some lookup tables we need to fill in core and abstract machine language, so we'll do those. I think there's code that automatically translates some of them, unless they're explicitly defined. So let's just quickly add these in. So this is what probably automates it. Yeah, for uint or vector. Yes, this is how it automatically translates, right? There's a lookup table for it. I've already done this far. Cool. We need to hop over into, where was it saying? The abstract machine language one. Fill in some more lookup tables. This is just for printing code when we debug. This wants to say if it has a return value. Yes, it does. Okay, cool. So, right, we're nearly there. Just got to edit the SPIR-V file now and just tell it how to write out to a SPIR-V file, like what instruction it needs to use. So in SPIR-V generation, there's the bit LSB thing. I think it can just use the same thing. So there's a, where does it get the, right, yeah, here's the, how it looks up the, oh, no, it's got to be a different one. It can't do this. Right, what's the closest thing to it? Because those ones are using the GLSL standard library, but it's not in the standard library. It's actually in the, oh, there's too many windows in my face. Oh, there's bit reverse as well. Ooh. I've never needed a bit reverse. But yeah, it's in here. Do I use that bit field? No, I've not used it. So we might put one on it on its own. But where does it just have a... That's a GLSL extension. GLSL. Any bit or... There's a for loop. Okay, so what is that? So 0 is the return type. Yep. Then it just translates that. But yeah, so this one should do it. So we just want to add one for bit count. So we need to add a new enum for SPIR-V up bit count, which we'll do that in just a second. So yeah, that's nearly it. So we should just be able to do something like, whoops, smash, 205. So where's 205? Where's the hole for that? Here. Boom. So encodes 205 into the binary. So that should be it. We'll make a new build and then we'll bring it over into the code base. So to do that, we just launch the release script. Packages one up, optimizes it, packages it up. Latest Spivvy Cross has a, Spivvy Tools has a bug. So we ignore that. So not build, third party. So let's get the new HTTP binary in there. I need to do one for Windows off stream. I'll do that after the stream. Yeah, the HMaths libraries got updated. So HMaths needs to be updated. And kabam. Right, so everything's updated, and away we go. So let's get back into actually finishing off that. Oh, did we not? We didn't save a file. No. That's okay. So I have to recopy the binary over. Okay, so now I've got the binary copied over into the the game engine project. Boom. Now we're back, and we got this bit count function, which is just amazing. Actually, it might be missing like a generic thing, but it's fine. So I wanted to be able to count some bits. And then count some more bits. Right? And put that in a variable called spheres count, right? And count some more bits. So this is the exclusive LOD spheres. So I wanted to count for these ones as well, because when we're setting into the when we're writing into these clusters which have a full set of spheres. Wait, what's the way you want to do it? Do you want all the bits? Wait a minute, I'm a bit confused. We only want to we only want to say this cluster is full when 90% of the spheres exist, roundabout. That number needs to be tuned a bit. So you probably need all the bit sets. And then do the count. 1, 1. All right. How do I make this thing pretty? There you go. Very good. So that gets the spheres awesome together and gets a overall sphere count. So what we want to say is, like, you know, if there's like I don't know the perfect number. So you want to say, like, what is the mostly full cluster, mostly full spheres count? What is that number? So so apparently it's saying it's like 58. So we do 58 spheres for now. That's a bit over 90%. So I want to say, hey, if the spheres count is greater than or equal to, then go into here and write your cluster into the occupation map. Write the bit for your cluster in the occupation map. Excellent. Right, now we've got the custom downsampler. That one doesn't have to be changed at all. Cool. Now on the refine LODs thing. So the way this shader used to work, at least, is it used to start off at the leaf nodes again, right, and go up from the bottom of the tree. And then it would... Okay. So it starts off at the leaf... Oh, it is. What's my thing someone doing? Yeah, is that good? Right, so it starts off at the leaf nodes and it goes up the tree. Sorry. Processes each thread gets a leaf node. When the thread is done with that node, it will mark a little marker in there to say, hey, this child is done. And when when this one is completely finished and the last one that finishes writes this little marker there, it's the thread that can carry on and process that one and continue up the tree, do the marker, right? If it's not the last one to put the marker, the thread just terminates. And that's the way the strategy used to work. But since we don't have a list of leaf nodes anymore, because it just doesn't serve any good purpose, what's the best approach to tackle this problem? Now, we're starting off at the leaf nodes and going up. If that is the best strategy, we'll have another array, and we'll fill up an array of indices, and do it that way, and then we don't have to change much of the shader. So all this thing is doing, right, is it's going over each node, creating the lower LOD sphere for it. And you have to start at the bottom to do this, right? And then it's also then checking to see if the leaf node is completely surrounded by other clusters with a full set of spheres, and if using that lovely occupation map that we've built, doing it in a couple of samples and bit tricks, which is cool. And then if that's the case, it'll mark it, say, hey, we don't want to keep this thing anymore. And then okay. So if we're going to be doing this, we need to have an array of leaf nodes, which we can do. It's just the best approach, because you're going up from the bottom to the top anyway. And that's fine. We can do that. And the final shader, the make persistent shader, this copies the tree. So with this one, I did do the leaf node thing initially and traverse up from the bottom. But realistically, you only want to just start from the top. Yeah, do another ring buffer thing like we did in the other shader. So what I need then is a temporary buffer that we fill. Like, when we construct these leaf spheres, this right here, yeah, but then going up the tree is a bit of a bugger. Because we don't keep track of the visit bit, so to say if it's been visited or not, but we could, like, to say each node has been visited. We don't have that system anymore. We can have it in a separate buffer elsewhere. But I wonder what you would. So each node used to have a list of visit bits, one for each child, and you would know if all of the children have visited that node. Yeah, we'll do a mixture. We'll do this ring buffer idea, right? We'll do the ring buffer idea, but it's going to start off with a list, right? It's going to start off with a queue that's filled with the leaf nodes, and you're going to push on the parent nodes. Yeah, but how do you know if you're the last child that's visited? Well, because all of the queue will be processed. No, it won't. I was going to say it will be processed in order, but you have 32 threads coming by and picking up. Sorry, you would have like, maybe 32 or more compute units coming by and picking these things up. We might need another buffer accompanying alongside it to have the bits to say. You could do it in waves of LODs. You could place a marker in the queue, and it could be U32 max, take 1, or something like that. It's another marker. And that one means you basically wait there. Yeah, it's possible. You wait there until. You basically wait there until all of the queue has been exhausted. Something like that. Yeah, you wait there until the queue has been exhausted, then you carry on again. That's the way around the solution. Can't you just use a basic counter for this instead of a bit flag for each node? A basic counter. So you got to start out all the leaf nodes. And the leaf nodes are they're not contiguous in memory anymore. And then you have to go up the tree. Oh, you want to talk about basic counter? Yeah, you could use a counter, but yeah, I see what you're saying. Instead of the bit flags, you can use the counter. Yeah. The reason why I was using a bit flag before is because I had a bit set that I was squishing it into. But yeah, counter would probably just be fine. But the benefit is that I had eight children, and you only have it says 8 child nodes, and the cluster. Yeah, so initially with this children bit set, we're only using 8 bits. Actually, there's my bit set right there. But yeah. Anyway, so I was using the higher bits to sort of keep track of which ones have visited. And then I was just checking to see if they've all visited, basically, by taking some of the high bits, moving them down, and comparing them with the low bits. That's all I needed to know. But yeah, counter would just mean it'd be another variable, right, and just cost more memory. But yeah, I think we can adjust that refine thing. So all it takes is another queue, another process queue. So because the problem is you can't fill up. So should this one be called like volume constructor? All right, I'm sorry, we're gonna do this. We'll have two of them. Oh no. I just can't be bothered to name it. It'd be even longer. So process queue for the construct, and then the refine. For refine LOD, something like that, right? So when we're doing this, we can just do 0, 0. I don't know, man. Yeah, so it just simply puts one on the... Alright, maybe I'll give them better names. Because they're going to need to be passed into to the same shaders anyway. It will, wouldn't it? I was just being so lazy. Right, so this one is for construct, process queue, refine, process queue. There we go. Bit better. Construct, refine. Because not this shader, right? But let's volume. Wait, let me just save everything. Volume constructor construct process key, right? Let's get all those put in there. Because this one is gonna need 2. This is gonna need the refine process queue, which we're just gonna pop on. Pop those boys on. When we come across a leaf node, right? So in the shared, there's a globals structure, and we need to have, so there's a process queue head tail thing. Now again, we do a construct process queue, and then we do the refine process queue. Okay. So again, it's all in here and it's crazy, but we just have to do a bit of a cluster construct underscore. No biggie, that's all sorted out. So you repeat that. This will be for the refine. And this is set to 0, there's nothing that needs to be added in. So that's when you reset the constructor, the volume constructor. Not to be confused with C++ in any way. Right. So now you've got the separate queue. When we're in this construct leaf spheres, this says this means we have children. This means we don't have any children, which means we're a leaf node. So we basically take this code and we can just say, you know, like all threads are getting here, so we kind of just want to say, okay, if we're the first thread, something like this, and we'll use the refine. So we add it to the refine. But we need to add our current cluster node. I need to add a comment there as well. We found a leaf node, so add it to the refine process queue. Excellent. So that means that now we've got an array of leaf nodes all sorted out for when we do the refinement. So in the refine, we'll probably do a similar thing actually. It's going to be pretty cool. We'll do this sort of super crazy queue system. Yeah, we'll do the super crazy queue system, but it's gonna probably have a little bit of an extra thing on it as well. I don't know how good this idea is going to be, but screw it. Gotta give it a go. So we drop this in there, and then we solve all the problems. So first of all, the dispatch is completely wrong. Be 4x4x4 again. So process is one cluster per one cluster per thread group. So there'll be 2 waves running because it's 64, right? 4x4x4. So this used to be dispatch indirect. Won't be the case anymore. Yeah, we need a process queue. Maybe we should call this the construct process queue instead. Whoops. Oh, I'm glad I did that change because I didn't change that to refine process queue there. That'd have been a bugger. Right, so this would be the refine process queue. We need one of those in the in here. Yeah, this needs a good old change. We need the cluster nodes. No child indices are needed. We're not allocating any more nodes. Wait a minute, I just remembered. The way that we allocate the nodes is wrong in the construct shader. Crap. That's for later. The way we do it here is for later. In the globals, we've got like a next index. Let's just get this right. Here's where the allocate happens. So the next index. Yeah, we've not used that yet here. So, okay, 540. Right. So we simply just bump allocate from here. Since we're in builder space. So basically when we copy them into more persistent memory, we're going to need to use this code. Because it's shared between all of the stuff. But right now, we've pre-allocated like a big enough buffer to store the most complex volume, but then we're going to simplify it. And then we'll copy it to more persistent space. So this code here, oh shoot. Wait, why is that next index? And the count's not even used. So the next index. Oh wait, I did the wrong bloody one, that's why. Okay. Wait, next index. No, that one does get deleted. Yeah, it's this one here, which one uses tree nodes count. So it over allocates, it does. That'd be 8, so number's different. Root node, aka LOD 0, over allocate so that the other LODs has their 8 start at the multiple of 8. Yep. So this is the thing we need to bump allocate. Children count, wherever that is. Yep. So that will get us our start index, basically. Now, something to take note is this code. Yeah, I should be able to work that out quite easy. I've got it around somewhere else. So bump allocate. Using here as we are inside the constructor, which has a full buffer, which has a max size buffer for all the nodes. We simplify the tree. later so that we only copy a fraction of these out to we only need a fraction of these. Awesome. So now back to the refined thing. So for this refined LOD, we're going to be using the... Right, this is going to be a bit different. So these variables here that we use will be refine. Right. So this is going to take off the key basically, but I wanted to add that thing. I need to make sure I put this thing in tonight. If we take from the queue, or right, what's something we've got to do is if we take from the queue and there's a little marker there to say, hey, kind of wait until the queue's been exhausted or been processed before you continue, and that way you can guarantee all the children, like all the child nodes have been processed before you do any of the parents, right? So essentially just one LOD at a time, but not necessarily every leaf node is at the same LOD, but it just, yeah. Because you can have like, this is a LOD 1 for instance, and these are LOD 2, and these can all be leaf nodes, but you won't do their parents until all of the children have been done, right, and been refined. So we need to have a way to place in... So first of all, we want to place the thing in the queue, right? So I want to call this thing... We'll call it the little const there, right? We'll call it the refine mark. Not a really good name, but it'll be U32 max take 1. And this is a little special marker to say refine wait for children so you place one of these in. So is it refine process queue? Here we go. So we just basically want to insert one of those in. But you only want to do this providing that you are. This is quite difficult to figure out when you want to do it. Well, there is the downsample pass that happens. You could stick it in there. well, you know, this is when they all terminate right here, right? Yeah, you can do something pretty funky. You can say if... Right, I think I got an idea. We need to put this thing a bit further up. Define, so it's like a volume refine, wait for whatever marker, right, something like that. So this thing, where's the refine node at? Right, so you're plopping one of those boys in. There you go. So you want to take this with us, and on the return, you're saying, well, if you're the dispatch index, where I guess all equal with a scalar, I guess, 0. So they're all equal to 0, meaning you're the first sort of the first thread across all groups to get here. Put the marker on. Put that little marker on at the end of the key, which is sweet. So in that refine LOD thing, oh, we'll keep hitting that mic. Another thing that we need to kind of wait for in here is like, well, you've got your cluster index, and turns out it's this sort of marker, which is saying, yeah, wait until all of them have been processed before I continue. But then you have multiple threads coming in here doing the add. Maybe this isn't a good idea. Maybe this won't work. Maybe there's a different way of doing it. You might be able to encode in the high bits of every single thing like a generation number, and you just pull them back out. So you got generation 0 in the high bits. You need at most like 7 or whatever, so you can put it in the higher bits. So I think what you can do, so you get the current sort of like generation, I guess. Process generation. That'll be 0. And what you want to say is like, well, if cluster, so you get the cluster process generation, and that would just be cluster index shift right 24, right? It's in the high 8 bits. And you're just gonna say like, well, if this thing, like while, right, it's lovely, is not equal to, all right, this solves the problem. Let me delete that other stuff before we and we can put a comment to describe what it actually does. Right. Anyway, back to where we were. So so I want to say like this ensures that all children, all child nodes are finished before before a parent is processed. Yeah. So we're just saying here, like, while that's not equal to process, wait a minute. Has that process generation got to be more of like a global thing, isn't it? Yeah, I think that's got to be more in a global thing, like an atomic load. Volume, global volume, cluster refine process generation. So you want to stick that in the global somewhere. And you need to make sure that thing has been cleared out to 0 when you initialize the constructor. Alright, so that's in the globals already now, so all threads have access to that. So again, we'll just spin until all children have been processed. or potential? Do you spell potential? Yes. English. There we go. So there's a nice little spin. That's pretty cool. Just to make sure when we populate these guys in the future that we put the generation thing in there. So just got to be careful. Oh, we need to clear it out as well. So you say cluster index and equal 1, 2, 3, 4. There you go. So you clear out spin until all potential children for this cluster the process generation counter thingy, right? Cool. So that's really nice. I really like that a lot. So basically all of this code goes. Doesn't this make the parent wait for all the leaf nodes instead of only... Yes, exactly. That is correct. It's, yeah, maybe I should... Yeah, it's not just leaf nodes though, in a sense, because, yeah. Yeah, that is right. It's the easiest method I could do without using any extra memory, basically. So hopefully it's all right. It might be better to use more memory. It might be but it depends what the trade-off is, speed-wise. Yeah, because you're using atomics. Oh, wait. We need to make sure we increment the counter, isn't it? Like, if you've span here, like, cluster process generation, if it's not equal to that, yeah, you got to do the wait code, right? So what you're saying is like, you basically up this number. So you want to then just say, if they're all sat here waiting, up the number. Generation. And then you want to say if generation greater than or equal to LOD count, right? Because that's just meant the levels you have. Then you return. Now, the problem is you're going to have tons of threads coming by and doing this. Yeah, it should be right. Yeah, that'll catch it, hopefully. Double check it before I launch it at least. But yeah, so then you get your cluster index. Here it is. Set up LDS memory. Right, this is where we've got to heavily modify how this works because the way that we dispatched was different. But yeah. Right, I think I've got to put a pin in it here. So this is where I'll just say to do. So we'll resume here. Translate all the code below to using 4x4x4 clusters and this new ring buffer. New queue, process queue. Right. Excellent. Isn't she amazing? So, right. So basically, this is my last stream for like over a month now. Great place to stop. But yeah, so I'm away a whole of February, and I'm back on the 5th of March. So yeah, when we get back on the 5th of March, we'll carry on with this refactor. Unfortunately, I couldn't stop in a better place. But yeah. So yeah, no. Yeah, it sucks, man. But it's gonna be awesome because I get to go outside, enjoy some sun. Long time. But there's a Discord if you guys want to hang out in the meantime. Chat about programming and such. Yeah, that's basically where I'm going to be in that time. Have a good vacation. Enjoy your time. Stay safe. Thank you so much. Yeah, stop in the middle of the file, exactly. Yeah. In a month's time, I've got to remember. Gonna be fun. But, yeah, it should be alright. I trust myself. You got to remember where I was in this refactor and the plan and everything. It'll be fun. But yeah, let's find someone to raid. Mr. Togglebit. Raid Toggle for a while. But yeah, have a good rest of your week, everyone, and also have a good, I guess, whole of February. I'll see you all back in March. And thank you for coming. And yeah, catch you later.